Namaste. Okay, today I'm going to talk about section 12.2. All right, and we'll see how this goes. If you're like me right now, then you're probably, I'm just exhausted. I'm just completely mentally exhausted. So, which was that mean? That means I'm probably going to screw up half the things that I'm saying to you on this video. So just kind of bear with me on that. All right. All right. So we're going to talk about theories of motion. And you're probably saying, like, what's the big deal with, like, why would you want to talk about theories of motion? Well, because moving is important to human beings. It is, right? When you are born, all right, within a few months, it's in your DNA to start to move and you start to crawl. So as soon as your body starts to get strong enough, you flop over on your belly and you use your arms and kick your legs and you try and move. Okay, that's in your DNA to do that. All right, it's very important. It's psychologically also for human beings to be able to move. And if you don't believe me, think of having a tragic accident and being paralyzed from the neck down. All right, for many people that I don't know of anyone who would say like, oh yeah, I'd be totally fine with that. No, you wouldn't. All right, because just to get up and walk from one place to another makes us feel good. Okay, and human beings also have this need to explore. We feel it. All right, we got to get up, we got to walk around. You've done this when you were a child. All right, you got up, you pulled yourself up, your legs got stronger, you started to walk around, and as soon as you did, you became a real headache for your parents because you started to explore things and you started to run away from them to go see what's over here and what's over here and that sort of thing. Okay, and it's important to us, and it's important to us as a culture, because movement means trading. Okay, almost everything you have was not made by you or anywhere around your house in this current year, in this current culture. Almost everything we have and own was made by somebody far away and shipped here. And this is not just true of Americans, this is true around the world. Okay, I mean, to different degrees. Obviously, in first world countries like us, almost everything we have is like we didn't make. It was made by someone else thousands of miles away. If you're maybe in not a first world country like like Liberia or Cameroon or Ecuador or something, you might have more things around you that you did actually make yourself or locally or things like that. But you still probably have a lot that came from far away. Human beings move, all right? We have always moved. We've moved from when we were very primitive in our species. We followed the animals, all right? We were nomadic, all right? And we needed to do that to survive. The animals move, well, we got to go over here now, and so on, okay? And we have this need to explore. So movement is actually very important to us. It's in your DNA to do that, okay? All right. So let's talk about this. All right. Well, first there was this guy. The first real written theory of motion comes from this guy. Now, by the way, I'm sending you the slides, so make sure you're taking a look at them. All right, from this guy named Aristotle. And Aristotle was a philosopher. He wasn't a scientist. The difference being he didn't test out his theories, really. And what Aristotle said, now he was also, by the way, just to further your education, he was part of a lineage of great teachers. His teacher was another philosopher named Plato. And Plato's teacher was probably one of the most famous and one of the greatest teachers in all of human history, named Socrates. So it was Socrates who taught Plato, who then taught Aristotle. So you have these three great sage-like teachers and thinkers in human history. What Aristotle said was that all things come to a natural state of rest. Okay, and that's what Aristotle said, and he was absolutely wrong. Okay, but he didn't know it at the time, and also you have to consider the fact that the guy was living 25 centuries ago, and don't go thinking he was stupid. He was extremely intelligent. probably genius level intelligence, all right, easily, based on what he wrote and the thoughts that he had and so on. But on this he was wrong about. But if you don't test it out, just based on general observation, it seems to make sense. Just like a flat Earth seems to make sense. I mean, if you look around you, it doesn't look like you're living on a giant ball. And what Aristotle observed is that when you throw something like a rock, what does it do? Well, it goes for a little bit of time, it hits the ground, and eventually stops. If you push like a chair or something, what does it do? It slides for a little bit and then comes to a stop. So Aristotle's conclusion was that things naturally want to not move, and if you move them, they will naturally go back to that state of rest. Okay? And, he was, which is pretty smart. He wrote that down. All right, it seemed to make a lot of sense, all right, until literally over 1,000 years later, this guy comes along, and I'm going to spell his name wrong, so I'm checking my notes. All right, an Italian scientist, and he was an early scientist 500 years ago. And he was also a very smart man. Now, what made Galileo a scientist as opposed to just a philosopher is Galileo took the next step in the scientific method, and he tested things out, okay? And so what Galileo thought was this, and what he observed was he would take and he would make ramps, and he would take musket balls, usually made out of lead and kind of heavy. And you notice that, all right, so if I roll the musket ball down here, what's it going to do? It's going to go down, it's going to pick up speed, and it's going to go uphill. And he made a note, all right, that where did it go to? It went to basically whatever height it started from, vertical height, okay, on the other side of the ramp, on the high side of the ramp. So if you started from this height, it would go up to that height, maybe a little bit less, but he said, well, there's this kind of resistance in the wood, and that was the first concept of friction, all right, and so on. And then he tried this. He said, well, that's interesting. What if I do this? And I lengthen this side like that, okay? So I'll make this less steep. And he noticed the same thing. It would just go longer until it reached pretty much the equivalent height. And if you made the ramp even longer, and make sure you guys are getting this, by the way, because this is a good example of how somebody who's smart thinks. And you need, if you're going to think well, you need to be exposed to that, okay? Some of the greatest thinkers in humanity, why were they the greatest thinkers? Well, sometimes they came up with some of the most simple experiments that wound up becoming great conclusions. Anyway, so if I made it even longer, what would it do? It would go even further. So Galileo said this, well, what would have happened if I never let it get up to their original height? If I just made this flat and there was completely no resistance in the wood, no friction in the wood, what would it do? Well, Galileo said, well, the ball would roll forever because it could never go back up to its original height, so it would just roll forever. So Galileo came to the conclusion that all objects, all right, move in a straight line, continue to move. To move. And they move in a straight line at a constant speed. All right? And they don't spontaneously speed up or slow down. All right? Now, his theory, all right, well, initially people thought he was a bit crazy, but it kind of developed, over the years, it developed some credibility because of new discoveries that were happening about Galileo's time, mainly the fact that the Earth wasn't the center of the solar system, it was just another planet going around the sun. And so if it was just another planet, the question was, well, how does it move? All right, why does it move? The Earth doesn't have a big motor on it to keep it moving through space. And Galileo said, well, it moved because it was form moving. Maybe God made it move or something, but once it's moving, it just keeps on moving. And that's kind of true, all right? That's not kind of true, that is true. Objects in motion, if you set them in motion, they just keep on moving. This is radically different than what Aristotle says, the opposite. Aristotle said things will automatically stop. Galileo said, no, they're not. You set it moving, it won't automatically stop. Something has to make it stop. So if you're in outer space and you take a baseball and you chuck the baseball, what's it going to do? It's going to keep on going. It will never stop until something hits it or causes it to stop. Okay? All right. So then that's the second theory of motion. And then you have this third guy, all right, who happened to be born, by the way, on the same exact day that Galileo died in 1642. All right, and this guy was Isaac Newton. Now, normally, we would be spending a couple of classes just talking about Isaac Newton and his history because it's very interesting. He had a really crappy childhood. All right, he was a premature baby. His father died before he was born. Okay, he didn't have a very good childhood and so on. All right, but so he was very interesting just as a person. All right, but what Isaac Newton did was he came up with 3 laws about motion, which holds true this day. And as far as we know, Isaac Newton's laws of motion are the way the universe works. They've been modified in 300 years, namely by a guy named Einstein. Okay, but the basic tenets of what Isaac Newton said seem to hold true. So we think that he kind of provided some insight into the very universe itself about how things move. Now, what Isaac Newton's laws enabled human beings to do is not only explain how everything moves, but predict how everything moves, which is even more important. Okay, so for example, if you shoot a cannonball out of a cannon, where is it going to land? And you might say, who cares? Well, the armies of the world cared in the 1600s and 1700s, and Isaac Newton's laws enabled a whole ballistics and gunnery technology to take place, and that's really shifted the balance of power in the world towards the English nation and eventually led to the creation of the British Empire, because they were able to make very accurate cannon that hit you the first time. And if you're in a war, whoever gets hit first loses, and the British were able to make extremely long range and accurate artillery, okay, which shifted the balance of power on the entire planet based on his work. Now, did Isaac Newton mean to create weapons? No, he didn't. It was just a way of employing the knowledge that he came up with. By the way, also his 3 laws are the basis for our engineering technology. It's the reason why we can build buildings like over 10 stories high, right? If you lived in the early 1800s, New York City was flat. It was a flat city. We were still developing the engineering technology based on his 3 laws of motion. Now we can build these huge buildings, and we have the ability to make these huge or awesome vehicles like aircraft that travel much faster than the speed of sound. And we can put rockets into space and satellites into space, and human beings can go to the moon if we want. We go to Mars if we want. Why? Because of his 3 laws of motion. Okay? All right, so anyway, the first law is the law of inertia, which is written on the slides. But basically, the law of inertia is a restatement of what Galileo found out, that objects want to move, objects in motion stay in motion. Write that down. I'm running out of board space. Objects in motion stay in motion. Objects at rest stay at rest. So what that means is if you're at rest, you don't spontaneously start to move. If you're in motion, you don't spontaneously speed up, slow down, or turn. Make sure you have that. Replay this if you need to. And that's the law of inertia. The second law of motion is a mathematical equation, all right? And it relates acceleration to force and mass, okay? And what this says is that the acceleration of an object is proportional to how much you push it. That's what a force is, okay? Forces cause accelerations. That's in the previous video, okay? So the bigger force you put on an object, the more it accelerates. And if you think about it, if you take a softball and you throw a softball and you just kind of like chuck it a little bit, it's not going to go as far. But if you really haul off and throw it, it's going to go farther. Why? Because it's a bigger force. Bigger force, more acceleration. And it's, listen to language, inversely proportional to the mass of the object. So for a given force, what this means is the bigger the mass, the less acceleration. And that's why it's on the bottom of the fraction. Fractions work that way. The bigger this number is, the less this number is. Just to give you an example, 1 divided by 1 is 1. 1 divided by 2, I just made this number bigger, is 0.5. That's smaller than 1. 1 divided by 3 is 0.3, and so on. So the bigger I make this number, the smaller the overall number gets. Okay? And that's why mass is at the bottom of the fraction. And what this means essentially is, for a given amount of force, it's easier to throw a softball than it is a bowling ball. Why? Bowling ball, large mass. So for the force you can generate, you're not going to get it to accelerate as much as a softball. Why? Softball, smaller mass. And it all kind of makes sense. And to tell you the truth, you guys instinctively know these laws, okay? But just by being a human being and by moving around on planet Earth. The third law is action-reaction. Action, reaction. And what does that mean? That means, okay, so forces are created in pairs. Oftentimes, you have heard this law stated as, for every action, there's an equal and opposite reaction, okay? And another way of saying it is that forces are created in pairs. So when you push on an object, the object's inertia, because the object has inertia, resists your movement. That's what inertia means. When you push on an object, the object's inertia pushes back on you with an equal and opposite force. Now, a lot of people will say, okay, Mr. Bolus, I got that, okay? But what about this, Mr. Bolus? If you punch a piece of paper, didn't the paper punch you back equally and oppositely? But look, the paper just got killed and your hand hardly felt anything. Yes, it did push back equally and oppositely. But the mass in the second law has an effect. So when I push on the paper, does the paper push back on me? Yeah, with the same amount of force. And we both accelerate, but because the paper has so little mass, it accelerates much more than my hand does. Now my hand does slow down a little bit when it hits the paper. Okay? Remember, slowing down is an acceleration. It's a negative acceleration. So my hand slows down a little bit, but because the paper is so less massive than my hand, I don't feel it that much. Now, try punching a wall. Actually, don't try punching a wall, because you know what's going to happen. Why? Because the wall is attached to a building, which is much more massive than you are. So for the given force, when you punch the wall pushes back on you equally and oppositely, but now since the wall is more massive than you are, you do most of the accelerating, not the wall. So the opposite happens. And your hand undergoes a massive deceleration, probably breaking a few bones in the fingers and the knuckles and so on and so forth. Tracking on that? Okay. All right. Okay. This video is getting a little bit long, but I want to make sure that I have everything to it, and I think I got it. Okay. Now, by the way, I know this video is 18 minutes long, but this would have been an entire hour-and-a-half lesson. And we would have done massive demonstrations, all right? Like, for example, when I talk about the first law, we do an inertia demonstration where I drag out the 16-pound shot put that I have in the room, and I have you try and lift it up like that, and you can actually feel the resistance, you feel the inertia of the shot put, and so on. Where obviously we can't do that. So this is kind of a short little thing, but I guess it's better than nothing. All right, so make sure you take good notes on the video. Do the worksheet 12.2, read your book, and also make sure you're taking a look at the slides that I gave you. Take a look at the questions too at the end. The questions will ruin your self-esteem. Okay, all right, so good luck with that. And see me during office hours with questions or for any help that you need. All right. So, and remember to enjoy yourself in this apocalypse. All right. Goal us out.